Welcome back, everybody. We're going to take a look at sections 5.6 and 5.7, both dealing with inverse trig functions. 5.6, we'll kind of talk about what are inverse trig functions, how do we define them, and we'll look at some derivatives of those. And then in 5.7, we'll look at integrals resulting in inverse trig functions, so going backwards, okay? So, first of all, it may surprise you that none of the 6 basic trig functions, sine, cosine, tangent, secant, cotangent, actually have functions that are inverses, and that's because they're periodic functions. They're not one-to-one functions. They're not strictly increasing or decreasing. We can see the sine function right here, right? That's periodic. It's cyclical. It has a pattern that repeats over time from left to right, okay? And this is a function in of itself. It's going to pass the vertical line test, but again, it's not one-to-one. It's not going to pass the horizontal line test, okay? Any of these. There's the cosine function. There's the tan function. All of these are functions. All pass vertical line tests, none of which will pass horizontal line tests, okay? So in order to talk about these things called inverse trig functions, what we have to do is restrict the domain of these original functions so that if we only focus on that portion, we will have a function whose inverse will also be a function. In other words, let's look at the sine function, okay? If I wanted to capture every possible value in its range, okay? Range values are y. Notice every value in the range is between -1 and 1, okay? What's the smallest interval around 0 that I could do that on, okay? Well, basically what I'm looking at is this portion right here, from -π/2 to +π/2. If I focus on just this portion of the sine function, that is strictly increasing, and if I restrict my domain to -π/2 to π/2, just that portion would have an inverse that's also a function. Okay, so if I ignore the rest of the sine function and focus only on this portion that I've highlighted, because that portion is strictly increasing, that portion would have a inverse that's also a function. So our restricted domain for the sine function goes from -π/2 less than or equal to x to +π/2. Okay, or you could use this kind of notation if you prefer. Okay, but the same thing. So the idea here is let's look at these trig functions and let's see, what portion of it would we need to just focus on so that it's strictly increasing or decreasing. And we always like to be near the x value of 0, okay? So looking at the cosine function, again, the range goes from -1 to 1. That captures all the possible y values, okay? The smallest interval around 0 that does that is the interval from 0 to +π. If I go from just 0 to +π, I have a strictly decreasing function. It hits every value in the range, and the inverse would also be a function. So if we restrict the cosine function from 0 to π, that will guarantee that the inverse of that portion is also a function. Okay? And again, just a couple different ways to notate that stuff. And with the tangent function, this is cyclical. It kind of always repeats this pattern that we see here. And from -π/2 to +π/2, we encapsulate every member of the range, which here the range is all reals. We could write that as all reals, or we could say -infinity less than y less than infinity. And if we, again, just look at the portion that I've highlighted that is strictly increasing in here, that would have an inverse that's also a function. And that goes from -π/2 to +π/2. But notice the asymptotes, so we don't include an equal sign here. Okay, we would use open interval notation if we wanted to. Okay, so again, when we talk about restricting domains, we're really just focusing on these highlighted portions of these original trig graphs so that we can consider their inverses also to be functions. And we just call them inverse trig functions, okay? Definitions of inverse trig functions, okay? There are 6. There's an inverse for all 6 original trig functions, but we're just going to focus on 4 of them here. Okay, and the first 3 go exactly with the 3 that we looked at up above, and then I've also thrown in the inverse cotangent function down below here as well. But okay, so look, where it says function in this table, there are basically three ways of writing inverse trig notation, okay? So in the first one, we have y equals the arc sine of x. That's ARC sine of x, okay? Arc sine means inverse sine. Another way to write that is with that, what looks to be a -1 exponent, okay? That is inverse function notation. You saw that in a previous lesson when we looked at inverse function notation like that, f -1 of x, okay? It's the same idea. When you see a -1 above the trig function, it means the inverse of that trig function, okay? And again, with the whole idea with inverses, we flip x and y. If I started with y equals sine of x, if I was to flip the x and the y, we get x equals sine of y, which is that version right there, okay? So look, we are responsible for three different ways of being told we're dealing with an inverse trig function, okay? It's either going to be y equals arc sine, y equals sine with the little, what looks to be a -1 exponent, but again, that means inverse sine. That's what we say. We say y equals inverse sine x here, okay? Or x by itself in terms of y. Okay, so in any event, if we're dealing with the inverse sine function, look, the domain and range are just the flip of the domain and range of the sine function, okay? So here, if the original sine function has a range of -1 to 1, well, now the domain of the inverse is going to be -1 to 1 for x. If the if the domain of the original restricted sine function was -pi/2 to pi/2 for x, then the range of the inverse would be the same, but for y, -pi/2 to pi/2 for y, okay? And so that's what this table is giving you the details on here for the four inverse trig functions we look at. For number 2, we have three ways of writing the inverse cosine function. Y equals arc cosine of x, x equals cosine of y, or y equals inverse cosine of x with the exponent. Again, the flip of the original domain, a restricted domain and range, gives us a new domain of -1 to 1 for x and a closed interval of 0 to pi for y. For number 3, the arctan, inverse tan, or x equals tan y function. The original range was all reals, so here the domain is going to be all reals. And the restricted domain was -pi/2 to pi/2 open, and so here that is what the range is. And the one I didn't draw, but hopefully you'll take my word on, is the inverse cotangent function down there below. Same domain, but that's going to have the opposite range. More goes with cosine from 0 to pi. Okay, remember, tangent is sine over cosine, and that's kind of why the sine and tangent ones are similar. Cotangent is cosine over sine, and that's kind of why the cosine and cotangent domain and ranges are similar as well. Okay, again, this isn't any big major things you need to memorize. You need to understand this notation, okay, and then understand how to do the kinds of problems we're about to look at. Okay, so when we talk about evaluating inverse trig functions, we're really talking about like what is the angle that's going to kick back this kind of y value that would have been in the sine or cosine function. Okay, so let's take a look at evaluating. So we're going to figure out what is the arc sine of -1/2, the arc cosine of 0, the arc tangent of radical 3. Okay, so the idea is this with these things. Look, I'm going to set these equal to y. I'm going to say, look, let y equal arc sine of -1/2. Okay. And so I'm looking for a y value that's going to have to be between -pi/2 and pi/2 for the inverse sine function that would have had an x value of 1/2. Okay, that's what I'm looking for here. So what I like to do is kind of rewrite these things, okay? Basically, the idea is this. There's different ways we could go with this. If y equals the arc sine of 1/2, what that means, okay, so that arrow means there's an implication here. This implies that the sine of some angle y equals -1/2. All right, when we're talking about the arc sine of -1/2, we're basically saying what angle of the sine function is going to equal -1/2. And there's a lot of places where sine equals -1/2, but we're, again, restricted to this range, okay, -pi/2 to pi/2. All right, so basically we're just asking, where does sine equal -1/2? And if you're pretty good with your trig values, well, it's the sine of 30 that equals 1/2. In this case, we're going to go back to -30, but we always use radians in this class, so we would say, oh, well, y is -pi/6 here. All right, so that's kind of one way to go about this. With the implication, if you prefer a more algebraic technique, okay, what can you do to get rid of an inverse trig function? Well, to get rid of inverses, you apply that thing's inverse, right? So look, I'm going to rewrite this like this. I kind of prefer this notation. Okay, the -1 exponent. That's just the way I like it. But what I can actually do now to get rid of this thing is I could actually take the sign of both sides. If I take the sign of the left, I'm taking the sign of the right. And inverses cancel, leaving us with that -1/2. So we end up with the same kind of conclusion here, is that if we start with this, then that's what it means. We're looking for the angle y where sine equals -1/2. And again, you really need to study up on your unit circle values, and again, know how to restrict your domain. Okay, the angle closest to 0, where sine is equal to -1/2, is at -pi/6. Okay, and that would be our answer here. Let's take a look at part B. Arc cosine of 0. So again, I'm going to say, look, let y equal arc cosine of 0. All right, and let's solve. So I'm going to rewrite this. I'm going to apply the cosine of both sides, and that's what gets rid of the inverse. So again, I'm saying, well, where does the cosine of a function equal 0? Where does cosine equal 0 between 0 and pi? Okay, well, where does that occur? It looks like it equals 0 right there, and that's right at pi/2. Right? We're basically asking cosine of what equals 0. That's what this is asking. Okay, the cosine of what angle is 0? Well, that's pi/2. Cosine of pi/2 is 0. And there's our evaluation. And last of these examples, arc tan radical 3. So again, I'm going to go y equals the inverse tan of radical 3. I'm going to apply the tangent of both sides. The tangent of y equals radical 3. So again, got to know your trig values. We're basically asking, at what angle does the tangent function equal positive radical 3? Excuse me, and we want to make sure we're on this interval. Okay. In the first place, tangent equals radical 3. So call that radical 3. We're basically looking for that angle right there. Well, that's at 60 degrees, or what we would call pi/3. Okay, so that's evaluating these things. You're really just saying, look, at what angle does this particular trig function equal these numbers, these radical? Where does tangent equal radical 3? Where does sine equal -1/2? Where does cosine equal 0? Okay, and we're getting those associated angles. Using right triangles, you can see problems like this. Given y is the inverse sine of x, and y is an angle in the first quadrant between 0 and pi/2, find the cosine of y. Okay, so again, y equals arc sine of x. Y equals inverse sine of x. What does that tell us? Okay, well, it tells us then, if we take the sine of both sides, the sine of y is equal to x. Okay, well, what does that mean? Okay, and how is that going to help us find the cosine of y here? Well, let's take a look. All right, inside the trig function is the angle. So y represents an angle here. Let's draw a right triangle. Let's call this angle y. Now we know the sine of y equals x. Well, think back to SOHCAHTOA. Sine is what? Opposite over hypotenuse. So if we know the sine of angle y is opposite over hypotenuse, and we know that the sine of angle y is x, they're giving us opposite over hypotenuse. Look, x over 1, x is opposite, 1 is hypotenuse. So I can label this side x, and I can label this with a 1. Okay? All right, and now what we want is what? Ultimately, we wanted the cosine of our angle. Well, cosine is going to be adjacent over hypotenuse, right? So the cosine is going to be the adjacent side over 1 here. So let's see what we get. Cosine of y is going to equal something over 1. Let's figure out what the adjacent side is. How are we going to do that? Well, we've got a right triangle. We can use Pythagorean's theorem, okay? So I'm just going to call the adjacent side a. And I can do, look, a squared plus x squared equals 1. And I just want to get this back in terms of x. So a squared is 1 minus x squared, so a is the square root of 1 minus x squared here. And that's how I would represent the adjacent side in terms of x. So adjacent over, looks like the cosine of y just is 1 minus, a radical 1 minus x squared when I simplify. Okay? And let me move this down a little bit and we'll try another one similar. Oops. Go. Given y equals arc secant of radical 5 over 2, find the tangent of y. Okay, so ultimately we want tangent of y given this bit of information. Okay, so again, look, y equals the inverse secant of radical 5 over 2. If I take the secant of both sides, I get this. And secant is really what? 1 over cosine. So if I take the reciprocal of both sides, I get this back. Okay, all I did was flip both sides. Secant is the flip of cosine, so if I flip this side, I flip that side. Okay, and so now we got it back in terms of a basic trig function we're familiar with, cosine. Okay, so we're told the cosine is radical 2 over radical 5. So let's draw the right triangle. Here's angle y. We're given adjacent over hypotenuse. So the adjacent side is 2. The hypotenuse is the square root of 5 here. We ultimately want the tangent of angle y. That's going to be adjacent opposite over adjacent. We want opposite over adjacent. Okay, so something over 2 because we know the adjacent side is 2. And again, let's use Pythagorean theorem to find the opposite side. I'll call that O. So 2 squared plus O squared equals radical 5 squared. 4 plus, I'm going to call it x, just because I don't like using O. It looks too much like a 0. 4 plus x squared equals 5. Subtract 4. Take the square root. It looks like x is 1. Okay, so in any event, we now have that, and now opposite over adjacent. Oh, that comes out nice, just 1/2 on the nose here. Okay, so again, given an inverse trig a value, you should be able to come up with other trig values by drawing right triangles. So again, you're using SOHCAHTOA and Pythagorean theorem for those, okay? And now to kind of get into the calculus of this stuff, let's talk about the derivatives, okay? Taking derivatives of inverse trig functions. I'm going to go through, one with you, and then I'm just going to give you like the formula for the rest, okay? So the idea is this. We want to find the derivatives of inverse trig functions. So let's suppose we have, y equals the arc sine of x. What is dy dx? What is the derivative of this thing? Okay, so look, I'm going to start by rewriting it using this notation. Okay, y equals inverse sine of x. Now look, we don't know how to take the derivative. This is not an exponent like we normally think, okay? So kind of here's what it's not. Dy dx is not going to be, chain rule, bring down the power, reduce 1 from the power, then multiply by the derivative of the inside function, which is cosine, okay? No, that's not what this works, because that -1 doesn't really mean a power of -1 in this sense, okay? So you got to be careful of that. Watch out for that, okay? But here's what we're going to do. Basically, remember, here's another way to write the inverse sine function, x equals sine y. Okay, so here's the inverse sine function in that form. Now, the benefit of writing it like this is that I can now take the derivative implicitly and get dy dx, okay? So let's take the derivative of both sides. Derivative left is 1. The derivative of sine y is going to be cosine y times dy over dx. And so now if I want to get dy dx by itself, I can divide both sides by the cosine of y. Okay, I'm just going to put that on the left, and I can write it like that. Now, that's okay, all right? And remember, my starting function is y equals inverse sine of x. It looks like the derivative then is 1 over the cosine of y. Now, the problem there is that here, is an angle, and in terms of x, now I'm working in terms of y. So we'd really like to get this thing back in terms of x if possible. And so here's how we do that, okay? Think about this, right? We have this little piece of information that x is equal to the sine of y. If I had a sine of y in my denominator, I could swap that out for the letter x. So, all right, I want to get an x in my denominator. To make that happen, I got to get a sine of y down there instead of a cosine of y. Well, how can I make that happen? I can use a Pythagorean identity to do that. Remember, cosine squared y plus sine squared of y is going to equal 1. It's your basic Pythagorean identity. So if I solve this for cosine y, let's see what we get. I'm going to subtract the sine squared, and I'm going to take the square root. Okay, and so I can replace cosine y in the denominator with the square root of 1 minus sine squared y. So here we go. And again, the reason we did that is because I can take the sine of y and replace it with the letter x. And it looks like I'm squaring it there. So at the end of the day, we get dy dx is 1 over the square root of 1 minus x squared. So if we start with y equals the inverse sine function, we get back 1 over 1 minus x squared, where x represents the angle inside of the inverse trig function. And then we could do a similar process with this to get the other derivatives of these inverse trig functions, but I'm just going to give them to you, okay? So you're going to want to get to know these and be able to recognize them. Here we go. Derivatives of inverse trig functions. Okay, and we're only going to study 4, okay? Inverse sine, cosine, tan, and cotangent, okay? So first up, I'm going to write it like this. The derivative with respect to x of the inverse or arc sine of u, where u is a function of x. Okay, we've seen this before. This is for chain rule, okay? So what we end up with, what we just saw, the inverse sine of x was derivative was 1 over radical 1 minus x squared. So here it's 1 over the square root of 1 minus u squared. U is what is inside of the inverse sine function. But then we got to multiply by the derivative of what's in the inverse sine function. That would be du over dx, we would write that as. Okay, so that's the derivative of what is inside of the inverse trig function. And we're going to do some examples, so you'll see how this works out in a moment, okay? Second up, the derivative with respect to x of the arc cosine of u is going to be negative 1 over radical 1 minus u squared times du over dx. Okay, it's basically the same as inverse sine, but comes back negative. Third, the derivative of the inverse tan function, arc tan x, or arc tan u here, is going to be 1 over 1 plus u squared times the derivative of u with respect to x. So notice it's not too unlike the derivative of inverse sine. The big noticeable differences are you don't have a radical in the denominator, and it's a plus instead of a minus. And the last one is the derivative of the arc cotangent of u, which, similar to how 1 and 2 work, is how 3 and 4 work. It's just the negative, the way it comes out of the inverse tan function, okay? So you want to know these, get to know these, okay? And let's see how they work. So let's practice taking some derivatives, okay? Let's find d dx of arc sine 3x here. Okay, so again, this is telling us take the derivative of this thing. That's what that instruction means, okay? So it's the derivative of the inverse sine function, and inside my u here is a 3x. So I'm going to get back 1 over the square root of 1 minus quantity 3x squared, all right, times the derivative of the thing inside. Well, the derivative of 3x is just 3. Cleaning it up, I put the 3 in the numerator, get radical 1 minus 9x squared down below. Okay, next up, d dx of, say, arc tangent of radical x. Okay, all right, so I want the derivative of inverse tan. This is what's inside there. Okay, so derivative of inverse tan, number 3 above. 1 over 1 plus the thing inside the inverse trig function squared times the derivative of radical x. Okay, so that's x to the 1/2. I'm going to get 1/2 x to the negative 1/2 back. All right, so here was the inverse trig portion. Here was the chain portion. Cleaning this up a little bit, let's see. Radical x squared is just x, 1 over 1 plus x. And then I can rewrite that as 1 over 2 radical x, this thing right here. And if I clean that up, I multiply tops and bottoms together. I just get a 1 in my numerator. I'm going to put a parenthesis around that and write it as 2 radical x quantity 1 plus x. And there's our derivative. Okay, and let's try one more here. Let's suppose y equals the arc sine of x plus x times the square root of 1 minus x squared, and we're going to find dy dx, okay? So a little more involved. Here goes. Dy dx equals, okay, derivative of arc sine, 1 over radical 1 minus x squared. That's just a plain x. No need for the chain rule, okay? Plus, well, a keen eye lets you realize we got to use what for the derivative of the next term? It looks like the product rule. Okay, so just watch out for that stuff. So the derivative of x is 1 times the other piece plus keep the x. Now for 1 minus x squared under the radical, that's a little chain. So I'll bring down the half, leave the inside alone, subtract, and the derivative of the inside, negative 2x there. Okay, so let's clean this up a little bit. We get the following. Let's see, plus the square root of 1 minus x squared. Here, let's see, the 1/2 and the 2 cancel. It looks like the whole thing's going to be negative. And this is under a radical in the denominator. And it looks like we have that x times x is x squared left in the numerator. And now this can be cleaned up a little bit. I mean, you notice 2 out of 3 of these terms have the same denominator. So let's clean this thing up. Let's get a common denominator. So I'm going to multiply the middle term by 1 minus x squared under the radical on top and bottom. And that's nice. Those will cancel. Give me 1 minus x squared up there. And now we have common denominators. I can put it all together over the common denominator. Looks like we get 2 minus 2x squared. And as far as I'm concerned, that's pretty good, but actually can simplify this. I can factor the 2 out. And something divided by its square root is the square root. So I could write it like that. That might take a little thought, but that's completely simplified if you want to take it that far. Okay. In any event, practice the derivatives, get used to the rules there, and watch out for the chain rule. Okay. All right. So now moving into 5.7, this is the integrals resulting in inverse trig functions. And you know what's nice is that we're only going to, there's really only 2 we need to know. That wasn't a very good line. Try that again. There we go. There's only 2, even though there were 4 derivatives we looked at. If you think about it, you know, the nice thing about these derivatives here is that, you know, 1 and 2 are just the negatives of one another. 3 and 4 are just the negatives of one another. All right, so to go backwards, we really only need 2 inverse trig functions to go back because we can just mess with the signs without much issue here, okay? So here they are, okay? So here are the 2 integrals you need to use. So we're going to say let u be a differentiable function of x. And let a be a constant greater than 0, okay? First up, the integral of du over the square root of a squared minus u squared. So radical something minus u squared. That should look more like the inverse sine one. Radical something minus u squared. It's not always going to be the number 1, so that's why we're writing it as a squared minus u squared for some constant a. In any event, this is going to take us back to the inverse sine function. But the way it works is we get the arc sine, and it becomes u over a plus c. Okay? And if you don't believe me, you can go ahead and take the derivative of this carefully using the chain rule, and you will get back something of the form 1 over radical a squared minus u squared, okay? But that's going backwards, and then to go backwards for the inverse tan function, we're going to look at that as du over a squared plus u squared. And this one ends up having, it's similar, it's the arc tan of u over a, but the way this works out is we actually get a 1 over a out front with that extra constant, where we don't with the inverse sine one, okay? And again, you could take a moment to try and take the derivative of this result and see that we indeed get back what's inside the integral, okay? But these are the two you gotta look out for. And again, what are we noticing? We're noticing, like, basically, you know, the variable squared, here's the variable u, okay? So we're looking for like u squareds or x squareds down in the denominator, and some sort of constant squared to go with it. In one case, we'd have a radical with the minus. In another case, we would not have a radical with a plus. So let's take a look at a few examples, and these can get a little tricky, I'm not going to lie, and a lot of them require you use substitution, and some can require them in fancy ways. But let's take a look. Let's start with something like this. The integral of, say, dx over radical 4 minus x squared, okay? So the fact that we have the square root of something squared minus x squared in the denominator is really giving us a big clue that we're dealing with the inverse sine function here when we integrate, okay? What I like to do is rewrite what everything is. Look, if this is my a squared, okay, if a squared is 4, then what does that make a here? A is 2. So now I know what I'm going to plug in there. That's going to be a 2 in that denominator. If this is my u, basically, if u squared is equal to x squared, then u is just equal to x, and du is just equal to dx. All right, so watch. If I take this original integral and I rewrite now, dx is going to get replaced with du. Radical is what it is. Now 4 was my a squared, and x squared was u squared. Now it's exactly this rule right here. You can literally write it out. That's going to be arc sine of u over a plus c, and now sub in your values for u and a. Arc sine, let's see, u was x, and a was 2. And there you have it, okay? And again, if it, take the derivative if you want to do a check. Now that we know how to take the derivatives of these things, right? The derivative is going to be, well, derivative of arc sine is 1 over square root of 1 minus whatever's inside the arc sine function squared times the derivative of what's on the inside. Well, that's just 1/2 x, so the derivative of that is a half. And the derivative of this constant will go away. All right. So look, I could write it like this. This 2 is in the denominator. And I could square the x over 2. And actually what I can do is, look, you can it's hard to distribute into a radical, but look, you can distribute radicals together. A radical can be distributed into another radical. So if I want to find a way to distribute this 2 in, just to kind of, basically what I want to do is make sure I get back exactly what I started with up here, because they are the same, but I want you to see that, okay? We're taking the derivative to check our work. So here's what we got to do. I got to rewrite 2 as the square root of something. Well, 2 is the square root of 4, isn't it? Now I can distribute the square root of 4 in. 4 times 1 is 4. 4 times x squared over 4 is x squared. Sure enough, I started with exactly, I got back what I started with, okay? So again, these are going to be tricky. It's going to take some practice, but let's go through a few examples, and hopefully you'll get the hang of it, okay? Okay. Next up, let's take a look at the integral of, say, 4 over 1 plus 16x squared dx, okay? So you see the x squared, something plus x squared in the denominator, you should be leaning towards the inverse tan function here. Now, again, we got a lot of integration rules come our way. You might think u sub to begin with. Oh, let me try u sub. If I let u equal 1 plus 16x squared, then the du is going to be 32x dx. Now look, I don't care about the 32 so much, but do I have an x times dx left up here to make that du work? No, I don't, okay? So regular u sub's not going to work here. And then we think, oh, wait a minute, I got something squared plus something squared in the denominator. So this is probably going to be inverse trig, okay? So look, again, I kind of look at it like this. This is my a squared. This is my u squared. If a squared equals 1, then a is 1. If u squared equals 16x squared, what does that make u? Take the square root, you get back 4x, okay? So, and don't forget du. That's going to be 4 dx here. And so, if you think about it, that's exactly what's inside that integral. So watch what happens here, okay? 4 dx is my du. A squared is 1. I'm just going to write that as a squared plus the u squared. And now I have exactly that rule, number 2. So I'm going to get back, following the rule, 1 over a, arc tan of u over a plus c. And now I'll replace with what a and u are. So I'm getting 1 over 1. Arc tan of 4x over 1 plus c, or in other words, inverse tan of 4x plus c. Okay, that's how that one comes out. And again, if you want to do a quick check, if I take the derivative of this thing, derivative inverse tan, 1 over 1 plus whatever's in there squared times the derivative of the inside, sure enough, I'm getting back what I started with. Okay, try another. Suppose we have something like this, dx over 2 plus 9x squared. So again, we see something plus something squared in the denominator. We should be thinking inverse tan. So again, this is my a squared, this is my u squared. If a squared is 2, then a is the square root of 2 here. If u squared is 9x squared, taking the square root, we get that u is 3x, du is 3 dx. Well, I just have a dx in the numerator, so I got to make sure to move that 1/3 over. Okay, so rewriting this, my dx in the numerator was 1/3 of a du, and I know my bottom is in the form a squared plus u squared. That's what I chose, okay? So I know I'm going to get back, well, let's keep the 1/3. I'm going to get back 1 over a, arc tan u over a plus c. 1/3 times, okay, a is radical 2. Arc tan u is 3x here. 3x over radical 2. All right, so 1 over 3 radical 2, if I want to clean that up just a little bit. And there's the end result. And it's fine to leave radicals in the denominator in this class, okay? You don't have to worry about that. All right, so there's kind of like, what I would call, some basic ones, okay? Let's take a look at another here. Let's suppose we have the integral of, say, dx over the square root of 3 minus 4x squared. So again, we have the square root of something minus something squared. We should be thinking inverse sine this time. A squared is 3, so a is the square root of 3 here. U squared is the 4x squared, so u is going to be 2x. And du 2 dx, and so dx 1/2 du, right? We just have a 1 dx in the numerator there. So rewriting this now, the dx in the numerator became 1/2 of a du. In the denominator, we're writing that as radical a squared minus u squared. So keep the 1/2. For inverse sine, we get arc sine u over a plus c, 1/2 arc sine, in this case, 2x over radical 3 plus c. All right. Okay, and now a few more that are going to require kind of a fancier u sub, okay? So here we go. And pause, rewind, reach out with questions if you have them. Okay, so we have the integral of x over quantity x to the fourth plus 25 dx. Now, this looks a little different in that we have like x to the fourth down there, okay? Again, if you see this on like an integral exam, you're not going to necessarily know right away this is inverse trig. If you try u sub, letting u be the denominator, that doesn't really work because we get an x cubed for the dx, which we don't have. We have x to the first dx, so it's not going to match. Okay, but again, when you see like things that are like in the denominator, something squared plus something squared, or something under the radical, something squared minus something squared, that's your big hint that you're dealing with these inverse trig derivatives, okay? So think about it. Again, if this represents, you know, that's the x portion, so that's the u squared portion, and there's the constant portion, okay? And it's just kind of flip-flopped with the commutative property additions, and you're not always going to see it. It won't always be the constant plus the x squared, okay? It can be the other way around, but let's take a look at what happens here. If a squared is 25, a is 5. If u squared is x to the fourth, what does that make u then? What did we square to get to x to the fourth? We squared x squared. So what would du be? 2x dx. Well, look, this will now pick up the x dx. Okay, so this is still going to be of the form something over u squared plus a squared. So in our denominator, we have u squared plus a squared, and then the x dx became 1/2 du. We get back our inverse tan integral. Keep the 1/2. We're going to get 1 over a arc tan u over a plus c. 1/2. What was a here? 5. Arc tan. What was u here? X squared over the 5. And just cleaning it up, we'll get 1/10 the inverse tan or arc tan of x squared over 5 plus c back. Okay. And 2 more to go. All right, let's suppose now we have the integral of e to the 3x over 1 plus e to the 6x dx. So again, we just had a lesson on e integrals. You know, we saw sometimes with u sub, if there's two e's, especially one has like a constant, you might be tempted to let that equal u. Well, du, the 1 goes away, and we're going to get back e to the 6x times 6 dx, or 6e to the 6x dx, because of the chain rule on this exponent, right? But we don't have e to the 6x dx left to pick up. We have e to the 3x dx to pick up. So again, this doesn't match out, okay? So getting a little creative again. Notice in the denominator, we do have something of the form a squared plus u squared, okay? If a squared is 1, then a is 1. If u squared is e to the 6x, what is u going to be? Well, what did we square to get back, you know, this thing, right? What did we have to square? How can I rewrite that as something squared? E to what squared? Well, it would actually be e to the 3x squared, because power to a power, you multiply, right? So u, if we took the square root of that, would just be e to the 3x dx, or just, excuse me, e to the 3x, okay? And that's what we seem to have here, okay? All right, don't forget about the du. That's important. We're going to get 3e to the 3x dx back. That will pick that up. Okay, and so with a 1/3, right? We got to move that 3 over. So rewriting the integral. Look, again, in the denominator, we're choosing to write this as a squared plus u squared. All that's left was e to the 3x dx. That ended up being 1/3 of a du. So once again, we have our inverse tan form of an integral. We'll keep the coefficient. We'll get 1 over a arc tan u over a plus c. 1/3, a was 1. Arc tan u was e to the 3x. All right, so end of the day, 1/3 arc tan e to the 3x plus c. All right, and again, take the derivative if you'd like, and you will get back what was in the original integral. Okay, and last but not least, let's do a bounded one. Suppose we have the integral from, say, 0 to pi over 12 of 1 over the square root of 1 minus 9x squared dx. So again, we look in the denominator, we see this square root of something squared minus something squared. We should be thinking inverse sine this time. If a squared is 1, a is 1. If u squared is that 9x squared, u is 3x, du is 3 dx, dx is 1/3 du. Now it's also bounded, so let's change our bounds over. U of pi over 12, 3 times pi over 12 is pi over 4. And u of 0, 3 times 0 is still 0. So new integral is going to go from 0 to pi over 4. The denominator is a squared minus u squared under the radical. My dx was a 1/3 du. So again, we've got now our inverse sine integral. We'll keep the 1/3. Here we get back arc sine u over a. And it's going to be bounded from 0 to pi over 4. So we get 1/3 arc sine of u over what was a? 1. So arc sine of u from 0 to pi over 4. So here we're going to have 1/3. I'm going to write it like this. Inverse sine of pi over 4 when I evaluate top minus bottom minus 1/3 the inverse sine of 0. Okay, so back to the evaluations. The inverse sine of pi over 4. What angle, what is the inverse sine of pi over 4? We actually don't know that, so I would just leave that. I was going for radical 2 over 2, but that's not right. The inverse sine of radical 2 over 2 is pi over 4, but not the case here. So we're just going to leave that as is. And what's the inverse sine of 0, though? The sine of what is 0? That's 0, so that we can evaluate and goes away. And it looks like at the end of the day we get 1/3 inverse sine of pi over 4. And we'd basically just be asking, what angle gives us a y value of pi over 4? That we don't know without a calculator, so we'll just leave our answer like that. All right, so again, some tricky stuff. I know we don't spend a lot of time on inverse functions or inverse trig functions, particularly in high school. But really the idea is to know how to take the derivatives of these things and recognize the antiderivatives leading us back. If you have any questions, reach out. And